All right, folks, continuing with the idea of limits to resolution and the impact on the double slit apparatus. So what you have is now an apparatus of slit width A and slit separation D. Okay, how is that going to impact what you see over here? Well, if we consider these two to be point sources, right? These two slits, which are not, and we had a huge discussion on that 2 videos ago, then we expect to see an interference pattern, right? I mean, some people call it interference diffraction pattern. Expect to see an interference pattern that looks like this. All these guys, all these fringes whose positions are determined by d sine theta equal to m lambda are going to be the same width, and going to be the same height, and going to look like this. Okay, and on the other side we have the same thing. This is not wider than the rest, same width. So they have the same width, the same separation, same everything. And this is an idealized interference pattern from a double slit where you don't consider the width of the slits. Okay? And now, okay, so let's make them all the same length. Right? So what happens now, and I'm going to paint this in red to indicate that this is coming from the slit width, okay? Not from the slit separation, okay? So the positions of the maxima are given by what? For interference, d sine theta equals to m lambda. So sine theta sub m for interference maxima is given by m lambda over d. So lambda over d, 2 lambda over d, so on and so forth, okay? What happens now, I'm going to make these guys the same width, same height. What happens now when you consider the slit width contribution, okay? I'm going to paint the slit width in green, okay, to show this different color scheme, right? Each slit, as we saw earlier, each slit is going to produce a diffraction pattern of its own. So it's going to look like something like that and something like this, maybe. Okay? But remember, these slits are so close to one another, they're so far that they actually merge into one, you know, it's not even that it becomes wider. No, I'm indicating here that they'll become wider. No, the fact is that these two envelopes, it's not that they merge and become wider. That's not true. What happens is that these two slits are so close to one another that these two envelopes are actually one envelope. They don't look like that at all. They look like, you know, just a single same width envelope as before from each slit, but they have coalesced into one envelope, one diffraction envelope, because the slits are. So basically what this is saying is that the envelope from this guy is here, right? And the envelope from this guy is coinciding with the first envelope because the two slits are so close to one another. So now the slit width contribution, okay? Can you now pause and see if you can draw the overall effect of diffraction and interference together? So what you have now, guys, is the following. Each slit's going to produce an envelope. The envelopes coalesce, so what we're going to have is the following, okay? You have this envelope here, and it's going to continue on this side here, and this is something really interesting in that this envelope, when you do the derivation of the intensity formula for interference and diffraction, incorporating the slit width into the calculation, when you do the integral, you'll realize that nothing survives outside the envelope. So this is really cool, and I think I have a demo recorded. I'll post that for you. It's got other things in it, that demo. I did it for it has a bunch of stuff. That demo has this stuff in it. It has some sound, you know, the demos that, you know, sound experiments that you know, gimmicks that I'd shown you before, and it has something on electromagnetism. It's really nifty. So your envelope, diffraction envelope, looks like this now. So you have a big envelope, which is actually this guy is, you can prove it, show it that this guy is twice as wide as these guys. Exactly. Okay? So it's very important. It's coming up in a quiz. So the width of this guy is twice as wide as, and each subsequent envelope, these envelopes, these secondary envelopes, secondary peaks, right? This is the whole envelope. So this main peak, the central peak, is twice as wide as these guys, and these guys are all the same width. I mean, up to a certain point. So what you will see then is a band. If you're looking at interference from a double slit, right? You know, let's say your double slit is arranged this way, like that. You have double slits like this, and you have light coming this way. If you have nothing else happening, you'll see this. Okay? If you just look at the idealized green laser, let's say, it looks like that. Okay? But in reality, what you'll see is, you know, a bunch of stuff in the middle. That's your central peak, and then there'll be a bit of a darkness here, and then a few here and a few there, right? And depending on the width of the minimum, you'll have, you know, a few here and a few there. But the key is now, you know, this guy will be twice as wide as these guys, right? And all these guys are going to have the same width. Okay. So what do we have in terms of quantifying what's going on? The angular position of the first interference maximum, this guy. So what do I label this guy as? This is theta 1 interference. And the position of theta 1 interference is given by 1, m is 1, lambda over d. Okay, guys? Okay, and there'll be 2 lambda over d, 3 lambda over d, so on and so forth. Okay? So up here, I'll have m. Let's say 1, 2, 3, 4, 5, 6, 7. This is m. So in this case, it'll be 0, 1, 2, 3, 4, 5, 6, 7. It looks like the m equals 7 interference maximum coincides with the first diffraction minimum. Right? So what is the first diffraction minimum? The angular position of the first diffraction minimum is this guy here, given by theta 1 diffraction, and sine of theta 1 diffraction is lambda over A, not D. And that makes sense. Why? Because D is bigger than A. This means that the angular position of the first interference maximum, it should be closer to the main axis or smaller than that of the first diffraction minimum. This will be theta 2, right? Sine theta 2, or it should be theta 2D. Yeah, this is theta 2 diffraction. And this is theta 2 interference. You have one here, one there, and this is also theta 2 diffraction. So interesting question, guys, is that, you know, where do we find, in summary, where do we find the diffraction minima? Diffraction minima are located at sine theta n for diffraction is given by n lambda over A. Okay, and within that you'll find sine theta interference, you know, maxima. I'm looking at the maxima only given m lambda over d. These are interference maxima. The I is for interference, m is for the order. These are interference maxima. And these are the diffraction minima. Okay? What I might not have time to do for you here, right, guys, depending, if I can, I will do it. We're running out of time. We have to, anyhow. So if I have time, I'll record it, I'll do it for you. If not, I have derived for you the interference pattern from a double slit apparatus, okay? But in the notes, there is a detailed description of the interference of the diffraction pattern from a single slit and from a double slit. Please look at those, okay? One uses phasors, right? To derive the diffraction envelope from a single diffraction, from a single slit, you can use phasors. There's a nice construct that, you know, you have to use geometry and whatnot to come up with an expression for the intensity from a single slit as a function of angle theta, there's you know, it's pretty straightforward. Just look at it, please, and it's really well laid out. It's very well done in the notes, and then you can combine that with the double slit interference pattern to come up with the intensity, realistic intensity from a double slit. Okay. For now, though, what I'd like to do is, you know what? Let's pause. Let's pause here. I'll take a little break, and then I'll continue with an example.